Welcome back, everybody, here on the stage in Zurich, and also welcome to everybody who is listening to us and watching on the live stream here in Zurich. We focus on AI and education, and I hope that you already have had new inputs and inspirations concerning that issue that we will discuss also this afternoon. Our next input will be about generalizable and interpretable models of learning. Our speaker is Tanja Käser. She is tenure-track assistant professor in computer science at the EPFL. She is heading the Machine Learning for Education lab. Before her current profession in Lausanne, Tanja Käser was, among others, a postdoctoral researcher at the Graduate School of Education at Stanford University. In her dissertation, Tanja Käser focused on user modeling and data mining in education. The dissertation was honored with the Fritz Kutter Award in 2015. After the input by Tanja Käser, you will have the opportunity to ask questions, as we do this the whole day, via the QR code or directly via the app, via the chat, so we can have a discussion afterwards with Tanja Käser. And so I'm very happy that you're here today in Zurich. Welcome here, Tanja.
So I think that's the clicker. So good afternoon, and thanks for the nice introduction. I'm happy to be here. My talk was announced in the program in English, so I will stick to English, but if you can also ask questions in German or English in the chat, doesn't matter. So today what I want to talk about is how to develop AI models that we can generalize across different settings and that we can interpret and then use them in educational settings. But first of all, let me quickly take a step back and tell you how I envision where we could use AI in education and which settings and contexts we focus on at my lab. So, of course, AI could interact with the learner, the teacher, and then also the researcher, but today we will focus mainly on these two stakeholders, the learners and the teachers. So, on the learner side, we are mainly interested in personalization, so using AI to provide a feedback that is personalized to the learner or to give a hint that is adapted to the actual state, to address also specific misconceptions of the learner or to generate tasks or examples that are appropriate for the actual, what I call knowledge state or strategies that the learner has at their disposal. Then, again, on the teacher side, we could, again, use AI to support the teachers at every level in classroom orchestration, so analyze the behaviors of the students in much more details than they might have time, and then report back to the teacher or recommend interventions. Of course, we could also support by generating content, grading exercises, grading exams. But what I want to focus on today is not this automation part where we use the AI to just automate tasks that the learners or the teacher would do, but where we use the AI to really augment the teacher's ability to individualize towards specific students. And so, providing this individualization requires that we somehow have, I call a learner model, so a model or a representation of the learner in our system. So that can be a representation of how much does the learner already know, what behaviors are they using, what learning strategies, how are they solving problems, so what do they have at their disposal. Then once we have that model of the learner and we can make predictions, we then of course have a second important step, and that is our model needs to interact with either the student or the teacher. That means we need to have a communication that is interpretable and intuitive among teacher, AI, and student. So, this learner modeling it can be challenging because of the educational context, because the learner model is here embedded in this context. So what do I mean by context? By context, I mean the learning domain. So what are we trying to teach? Are we teaching math? Are we teaching languages? Are we maybe focusing on metacognitive strategies? Are we teaching science? The curriculum that we have, the environment of the classroom. So is it used by one person, by a group? Is it used in a classroom? Is it used in a lecture hall where I have many students? And then the last part, which I called here learning sciences, but what I'm referring to is theory. So there is a lot of theory and knowledge, what is effective pedagogy and how humans learn. And when we now develop AI models, ideally, our models would take into account this theory and what we already know about learning. So from this, there are some key demands that I think are important for a good AI or learner model. And I will go through all of them, but not talk about all of them today. So the first one is just accurate and factual. Ideal, our model or our AI that models the learner or interacts with the learner should be accurate and should be correct. Generalizable, I will not talk about that today, but important in educational settings because we have very many different settings, we have different courses, and ideally we would not want to have a model that is specialized for a specific course and a specific teacher, but that generalizes across settings. Then interpretable, that means that when I have a learner model or an AI, I should understand why some predictions or decisions of this model are made. That is, on one hand, important that if I want to do an intervention based on that or change something, I should know what the problem was, and then to increase trust of the learners and of the teachers. Fairness, so the model should not discriminate, and then aligned to the context just describes the previous slide where we say an AI model is never used outside of a context. It's always in an educational context and in a course, and it should be aligned to what I want to achieve at this point in the course. And today, I will more or less talk about 3 of them, and how I will do that is by showing examples of our own research that we did in 4 different settings. So the first setting is in science education. So these are virtual labs where students can perform inquiry learning, so to discover mathematical relationships. The second one is a very different context. So the second one is professional or vocational education in Switzerland. So leading diagnostic conversations in a virtual pharmacy. And then the 2 last ones are both on supporting writing. So one is supporting the writing of procedural text with AI, and the second one, Reflectium, is about reflecting or metacognition, so reflecting about your own learning. And in each of them, the AI is used a bit in a different way, and in each of them we ensure, by combining different models, that our AI gives factual and accurate answers. And I will just jump into the first use case. So there, imagine that you are teaching chemistry here in a classroom, and your students have a virtual lab, and they interact with this virtual lab. So this would be, I'm not a chemist, I think this is Beer's absorption law, so how much light gets absorbed in a fluid. And this is simulated in this simulation, and basically what students can do is interact with it, set different parameters, and then observe the outcome. So this gives the opportunity to have a new way of teaching where we don't teach the equation first, but we let the students first interact with the simulation and see how much they can try, how much they can discover the underlying equation on their own, so through their own experiments. And we have used this with physics undergrads in the US, as well as with vocational students, so chemistry apprentices in Switzerland. And each time this is then embedded in a scenario. And what I will show now is the vocational education scenario task, because it is a bit more descriptive. So in the scenario for the chemistry apprentices, they are employees of a cantonal laboratory, and Migros is their customer, and they think something has been added to their drink mix, and they now need to compare different juices to references to figure out where something really has been added. So that's kind of the encompassing task. But on the technical side, what really needs to be done is that there are 4 flasks here, and the task is to use the simulation to rank these 4 flasks by decreasing absorbance of light. So what is now the difficult thing here is that you don't have to read the number, but is that the width of the flask that is indicated here cannot be replicated here in the simulation, and the same with the concentration. So you cannot just try these 4 flasks and then say that's the order, but the idea is that the students, or in this case apprentices, change here the flask width and then observe the effect on the outcome. So this is about finding relationships between variables and then quantifying them. And then we have done it very similarly with the physics undergrads, where it was a capacitor, and then you need to rank capacitors by stored energy. So the idea is that you need to find more or less the relationships between the variables, and then you can solve the task. As you can imagine, this is a hard task, not only for the apprentices, this was also a very hard task for the physics undergrad. So it would be nice if we could somehow support them right. So the idea here was, where does AI now come into play? The idea is, maybe while they interact with the simulation, we can figure out who will, in the end of the simulation, have discovered the relationships and who will not. So we try to predict after some time how well they will have done or how much they will have learned. So basically what we are doing here is we have the simulations and the students interact, and what clickstreams mean is that how the simulations save the interactions is not in human language, but it is something like clicked on this variable, increased this variable, changed this value, so every single detail. And on this, we now have an AI model, in this case a small neural network, and then we just predict based on this data, can the model be discovered or can it not be discovered? So at this point we can make a prediction, but it's not per se useful, because if we don't understand why the student will discover the model or not, we cannot really support them. So what we can do now is we have a trick here where we can interpret the inside of our model. I'm calling it now very untechnical, the inside of the models or our weight. So we can interpret or we can investigate what parts of these actions our model pays attention to and finds very important for the prediction. So for example, the model finds very important here that would be a green laser and a red fluid. So why is it so important in this case? In this case, that's so important to have this experimental condition, because if you happen to have the same laser color and the same fluid, no lights get absorbed, and no matter how you change the flask width, you will have almost zero absorbance, so you cannot really learn from this configuration. So we see that, for example, the model pays attention to that. So if we interpret all this together with strategies from literature, then for each student we have something like a list of good strategies. For example, this made-up example, the student only changed one thing at a time in the simulation, but then did not follow other strategies. So here we have not gone further, so what could we do with that? What we could now do with that is play this back to the student, or Also always interesting for classrooms, give an overview and then play back to the teacher which students are already proficient in which type of experimentation strategies. Okay, so the next one example is a context switch. So now we had simulations used in vocational education, or could also be used in high school, or as I said, we use it in undergrad physics or science classes, and it's not simple for our undergrad students to do this scientific discovery in the simulation on their own. The next example is really specific to vocational education. So it's a very simple environment. It's a pharmacy, a client comes in, and the only task is basically to support this client, so have a diagnostic conversation. And how this task can be done is by asking the client questions, by opening the compendium. That's a list, the compendium really exists. If you go online, you can check the compendium. You have all kind of medicine and their counterindications. And then the drawer, that is a learning tool because that's all the theory that students learn in class, or the apprentices learn in class. So now, this virtual pharmacy has about 20 different client scenarios, and where the AI comes in here is in 2 points. One point is offline, so the client scenarios and how the clients react has been generated using a large language model, so in this case GPT-4, and then aligned to the pharmacy assistant curriculum in Switzerland, and then of course done some refinement rounds, because in this case it's very important that all the medical details in the scenario are correct. So there have been expert checking by pharmacists. So that's offline. And then online, there are 2 AI models which support the apprentices by giving them personalized hints. And how does it work? The first model is domain specific. It's again a non-interpretable model which takes again all these action sequences in and then predicts a list of actions, so like 5 or 6 next actions that the student should take to in the end get to a successful end of the diagnostic conversation. Now, of course, these actions are not, while they are understandable, they are not very, I would say, useful for learning, because it's really saying, click the compendium to open, or open the documentation, or click there. So that's not really helpful if I'm just told to click somewhere and don't know why. That's why there is a second part, where in this case, GPT-4 gets the whole description of the environment, the whole list of actions and what they mean, plus important diagnostic strategies from literature. So important diagnostic strategies are, for example, to not do premature closure, so you always check all potential diagnoses and so on. And then it generates a nice hint from the student which comes on the side. This is one that I wrote. GPT has a bit nicer one than mine. So basically here it would say, oh, you already collected information about the baby, but it's important to take relationships into account. So here it's hinting towards asking questions about the baby's mother. And so basically what we have done, this has been tested in vocational schools, and of course, if apprentices in this scenario use the hints, they will have a better diagnostic conversation. So that is kind of clear. But what is interesting is the people who interacted with these hints and followed them in a next scenario, which is completely unrelated, will also have a better conversation and better strategies. So that was the second use case, and now we are again completely changing to 2 similar use cases, which are writing support using AI. And both of these use cases go a bit towards learning journaling or documenting learning. One is more for procedural text, and the second one for reflective text. So procedural texts are quite common in many professions, and also at universities, for example, writing experimental or lab protocols, right? That's a procedural text that needs to have a certain structure. And the example you see here is for recipes. Why did we do an example for recipes? Because chef apprentices, they work in a kitchen, and how they document their learning is by writing down the recipes that they already cooked and learned. And as you can imagine, that's not like the most favorite task that they are doing in their apprenticeship. So what we here are doing are generating personalized example. On the left side, here I can enter a recipe, then I click on Analyze, and then what I get on the right side is an example recipe, and this example is better than my example, so not better in taste, but it's better in terms of writing style, how it's written. It is relevant, so if I write about a dessert, it's again a dessert, and it has a similar preparation method. In addition, I get here all kind of tips which are marked, which the example recipe has followed, but I have not followed. So how this is done, again, 2 AI models working together, one domain specifics, which knows the rules about recipe writing and can take the recipe of a user and basically go through and say, follow this, did not follow this, did not follow this. Then a second one, which is then asked to generate a similar example based on the first one, and then again the first one coming back and doing these annotations. And this has also been shown to be helpful for learning, so improving recipe writing also when there is no AI available. And the key thing here is, one key intuition here is that I get an example recipe, which is similar to mine, but it's not mine. So I cannot just directly copy all the text from the example to improve my recipe. And then finally, there's a reflection space where they reflect. And then the very last example works in a similar way, and it's similar to, I think, something that the previous speakers talked about. When you have to write learning journaling and write reflections, you're supposed to write about, and here is reflection on practice. What did I do in this situation? How did I feel? What have I already done well? And what did I not do so well yet? Why was this? And what do I want to change in the future? And here we have a conversational interface, an AI chatbot, that basically goes through with the students. I would say, okay, describe me the situation first. The student will describe the situation. And so they go through the whole structure. And as you can see here on the left, it's also always covered which part that the student has already covered. And how that works is, again, 2 AI models, one that is fine-tuned for the task, so can recognize the structural elements in the text, and then a second AI model which is doing the conversation with the student. So these were the 4 examples where AI was used in very different ways, and we can see all of them were right now in vocational education, but 3 of them are also relevant to higher education topics. And what was done in these 4 examples was we always combine, as you saw, mostly it's not one AI model, but 2 AI models, where for one, it's not a large language model, but a small model where we know how accurate it is and where we can control it, and then combine with a large language model to make sure that we have accuracy and factual answers, and they have all been embedded in a specific context. And that was it from my side. Thank you very much for your attention.